Hello everyone, welcome to today's lecture. And today we are going to learn about heap. I'm not sure if you have heard this before, but I would say a heap is a very powerful but very little used data structure, and often students find that it is a bit confusing. Okay, so before beginning, I would like to tell what we are all going to cover in today's lecture. So, topics to be covered. First of all, that is most important, we are going to see how heap is represented. It's a representation in visual form and in implementation form. Okay, and this is the reason people do not understand it because there are different because of these two different representations. Okay, and we are going to see it shortly. After that, we are going to see what do you mean by Heapify. Again, there are two things: swim and sink. Third point, we would see a very important implementation of heap that is in the form of a priority queue. So again, you might get confused. Okay, how can heap be a queue? Because generally heap is represented as a cone or a tree structure, and queue is straight, right? But yes, we are going to uncover that also. And at the end, we are going to see the heap sort. Not very widely used, but yes, it has some very good properties. And during our this entire class, what I am going to do is I will keep on telling you few insights, few important points that you might want to remember for your exams, or if you are preparing for interviews, then maybe those can be a very good interview questions that I'm going to keep on telling you. Okay, so with this, I will not erase this part, but I will keep it for future reference so that we can say what we all have covered. Okay, so first of all, we are going to cover is uh, our representation. So let's move to first part that we are going to cover for today: representation of heap. So if you go to Google search and you say heap of grains, heap of anything of say sugar, it will give you something like this. Right? So this is the bottom of the heap and this is the top of the heap. It's kind of a pyramid structure or a cone structure that you can say. And that's how we visualize the heap. Right? I'm stressing the word visualize. So this is the visualization of the heap that we see. Right? But when it comes to implementation part, that part, it is an array. Right? Or a vector, whatever you can say. So it's a continuous stream of bytes in memory, right? That you can do a plus 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 and you will get to particular node. And how these two are going to be same, that's what we are going to understand now. Okay, so let's fill our data structure with any random elements. Okay, so we are not at all concerned about in which order they are. We will just see how the two things are represented. So let's see, I have in this array as 7, 4, 9, 1, 3, 5, 6, 2. Which number I missed? 8. Okay. Any order. So, if you want this to be represented in the form of how you visualize it, it would be, so let's see how we are going to visualize it in the form of the pyramid. So we will start from the left part. We will keep on writing and drawing the tree as the complete binary tree. Okay. So 7 will be the root, then 4, then we have to fill its right part, which would be 9. Then start with 4 to make it complete. We will write 1, 3, 5, 6, 2, 8. Okay, that's what we are. That's how we are going to represent it. Okay, this much should be good for our purpose. Okay, so now you can see that 7 has 2 child, 4 and 9, and the parent of 4 and 9 is 7. So that's the relationship that has been established by this tree representation. Right? By this tree representation, we have parent child relationships. Now you can ask me, okay, I can see this relationship in this tree because I have drawn these lines which are connecting these, but where this representation is in the format of this array. Okay, so there is a very basic formula for that, and that formula says, if you have to find out, so okay, before learning the formula, so let's write the indices for the array. 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? So our formula for finding out the child and the parent from the array goes like this. So let's say you have a node or an element at ith position. So to find left child, you will do 2 into I plus 1, and right child will be 2 into I plus 2. And if you want to find the parent, then you have to do n minus 1 by 2. And after doing this, you have to make sure, this is important, make sure the result is within array boundaries. Okay, so now let's see how we can prove this in our example, whatever we have drawn at the left hand side. So let's take the example which has both child and parents. So let's take the example of 1. Let's take the example of 1. So if you have to find the left child of 1, So what is the formula? So we are about the 1, so we will say left child 2 into I plus 1. So I here represent the position as I have mentioned. What is the position of 1? 3. Here is 1. Position I have written at the top. Position is 3. So left child will be 2 into 3 plus 1. We will get 7. What is at position number 7? 2. So this element would be 2. Right child would be 2 into 3 plus 2. Apply the board mass. It would be 8. Element at 8 position is, no, it's not 2. Element at 8th position is 8. Okay. Here. And if you have to find the parent, n minus 1. So n is, what is n here? Okay. It should not be n basically. Correction here. This should be I minus 1 because I am representing the index here. So I is 3. So it would says 3 minus 1 by 2. It will come out to be 1. And the element at position 1 is 4. Can you see how simple it is? We took the example of this node 1. So this example is corresponding to node 1 here. We are able to find the left child, the right child, and the parent. Right? And one thing that I told you about this array boundary. So for example, you want to find the child of 5. So what is the index of 5? Again 5. So I'm taking the example here. So let's say for element 5, index is, if you can check, index of 5 is 5. Okay. So if I find left child, it would be 2 into 5 plus 1. This will come out to be 11. Right child, 2 into 5 plus 1. This will come out to be 12. But both these numbers, they are greater than the length of our array. And what is the length of our array? I mean, the last index is 8. So that means, right, both child do not exist. So this is what we have to make sure. Right? So we can say children does not exist for element 5. So we have to make sure of this boundary condition. And one more thing that we have to take care is about finding the root. So as you can see from the array, you can get the root of every element, but not the root itself, right? So the boundary condition for root is if index is 0, then it is the root itself and there is no parent. Right? So this you can try. I am taking a pause here. If you have any concern, I would say rewind the video, go back and understand again. Because once you have this thing clear, you will not get confused in the heap data structure. And this we are going to use extensively. So wherever you are, if index is in your mind, you should be able to immediately calculate what is its left child and right child. Right? So I think that's what we have to cover for the representation part. Once we are done with our representation, so we can say that we have covered the visual representation and the implementation of also, that is in the form of array. So this part we have covered. Next, I am going to cover about the Heapify property. What is Heapify property? What is swim sync? These are fancy words, but there are better words also that we can use apart from these. So we are going to see about it. Okay. So if you are comfortable, you understood everything till now, you can continue. Otherwise, I would say take a pause here, see it again until you get absolutely confident and well versed with these representations. Okay, so let's move. This I'm not going to erase, but we can use the space below. Okay, so let's draw a line here so that we can have some markers. Now we are going to cover is what I meant by Heapify. So before that, we have to understand the property of heap. Okay. And before understanding the property, we have to understand or we have to know what are different types of heap. Because property will be based on the type. So before that, we will say types of heaps. The first is min heap and second one is max heap. Okay. When I say min heap, that means now I'm drawing in the tree representation, but when we will go for the implementation, it would be the array based. Okay. When I say min heap, that means the parent should be less than both its children. That means 4, this should be 6 or 9. Now this should be less, so it would be say 10. It can be 15. It can be 11. It can be 17. So this is a min heap. And when you say a max heap, the parent should be greater than both the child. Okay. So you can say 17. It should be greater than 9, 14, 5, 3, 12, 4. So this is a max heap. The parent should be less or greater than both the child in case of min heap or max heap respectively. Okay, so this is the property of the heap. So what we have seen in the representation above, we have just learned how to represent the heap. This is not a heap because you can see it is not following the property. I mean, 7 is neither smaller than 4 or 9, neither greater than 4 or 9. So we have just seen that as a representation. with any random numbers. But here, when we are going to actually see how the heaps look like, so it is like this, where we see there are two types of heaps, min heap and max heap. Now, from here only, we will move to our concept of what is mean by Heapify, right? So now going forward, for all our considerations, we will consider max heap only. For min heap, you have to just reverse the algorithm. That is not that much tough, and you can do that easily. But we will consider only the max heap for our all implementations going forward, right? So this is our example. Now you have to insert another element in this heap. Okay, so if I draw the array representation of it, it would be 17, 9. I'm just writing in the same manner in which it is appearing. 5, 3, 12, and 4. 0, 1, 2, 3, 4, 5, 6. We have to insert another element. So obviously, in an array, because that's how it is in memory, we can insert at the end only. Let's say that element is 10 at index 7. Now, this is no longer following the property of heap, because it will come out here. Why it come here? Because we have to fill the binary tree as if it is a complete binary tree. Now it is not following the property of max heap, because 10 is greater than 5. So this part is not following the property of heap. So we have to correct it. And this is called Heapify. So what if we see the definition, Heapify means rearrange the elements in the heap to satisfy the heap property. And our property of max heap is that the parent should be greater than both the child. It doesn't matter whether the left child should be greater or right child should be greater. That order doesn't matter. The parent should be greater than both. That is the property. And to satisfy that, we will do Heapify. Now, what will you do when you say, I want to Heapify this example here? So as I drawn, this is not satisfying our property. So what we will do is, we will swap these. So when I'm going to swap is, okay, let's write before that. So let's see what operations we are going to perform. Operations to Heapify. First operation, swap 10 with 5. Okay, so I am going to do is erase this thing. So 10 will come out here and 5 will come out here, right? And we will change the same thing in our array as well, because that's where the actually elements are stored. So we have replaced 5 with 10. So this will become 5 and this will become 10. Okay, great. Now we will see, okay, we have done the swapping, but now what has happened is this has violated our property, right? This has violated our property. So we will again do the swapping. Swap 9 and 10. So we are going to do the same thing again in the same manner. 10, 9. And we will do the same thing at our array also. This will become 10, this will become 9. Now, has our property satisfied? Is our property satisfied now? Yes, it is satisfied because 10 is less than 17. So, we will say finished. And as you can see, we have proceeded from bottom till up. If it is possible, we have not inserted 10, say 30, then we would have changed root also. Okay, so we are going from bottom towards up. This is called swim. In case you have done reverse, up from bottom, then it called sink, the reverse of it. If you want to insert another element, then you can insert that element at this position, say X, and then you will see, okay, if it is satisfying my property, then I will leave as it is, otherwise I will do the Heapify and change it. Okay, so in this video we are just understanding the concept. Okay, after that we will spend some time on understanding the time complexities. We will see why time complexity comes as n log n or log n for which operations, and then we are going to the coding part. We will actually code how all these Heapify works. And if we see what all things we have covered till now is, we have covered swim and sink, and Heapify we have also covered. So, and once you have understood Heapify, priority queue would be very easy for you. So in next video, we are going to learn about what is priority queue. Okay. So thanks for watching. See you again. Have a great day. Bye.